So welcome to my presentation. My name is Wang Hongfei. I come from Tokyo Metropolitan University, and my topic is Chinese grammatical correction using BERT-based pre-trained model. First, I want to introduce about grammatical error correction task. Grammatical error correction can be regarded as a sequence-to-sequence task. GEC systems receive an error sentence written by a language learner and output the corrected sentence. For example, in this Chinese sentence, which means people experience many things in their lifetime, the red part, which is a word selection error, is corrected into green part by the GEC system. For our main contributions in this study, we verify the effectiveness of two methods that incorporate a BERT-based pre-trained model into an encoder-decoder model on Chinese grammatical error correction tasks. We also analyze the error type and conclude that word-level errors dominate all error types, and sentence-level errors are yet to be addressed. We use the BERT-based Chinese pre-trained model called Chinese Robata whole word masking extended data developed by Cui et al. BERT used a methodology called the master language model. In this methodology, some tokens in a sentence are replaced with masked tokens, and the model has to predict the replaced tokens. As for main difference between Chinese Robata and BERT is that Chinese Robata used a methodology called whole word masking. In whole word masking, when a Chinese character is masked, other Chinese characters that belong to the same word should also be masked. Next, we construct the correction model using transformer and incorporate the pre-trained model in two ways as shown in this figure. The first one is called BERT encoder. The encoder of transformer is initialized with the parameters learned by pre-trained model, and the decoder is initialized randomly. The second one, called BERT-fused. This is the technique proposed by Zhu et al. In their method, input sentences are fed into the pre-trained model, and representations from the last year of the pre-trained model are acquired first. Then, the representations will interact with the encoder and decoder by using attention mechanism. We use the data provided by the NLPCC grammatical error correction share task to train and evaluate our models, and the number of data is just as we show here. We compare our methods with these three methods. Zhao and Wang proposed a dynamic masking method that replaces the tokens in the source sentences of the training data with other tokens. They achieved sorted results without using any extra knowledge. This is a data augmentation method that can be a supplement for our study. Fu et al. Combined a 5-gram language model-based spell checker with subword level and character level encoder-decoder models using transformer to obtain 5 types of outputs. Then they re-ranked these outputs using the language model. In their method, several methods were required and the combination method was complex. Ren et al. Used the CNN model. However, because the structure of the CNN is different from BERT, it cannot be initialized with the weights learned by the BERT. Here, we show the systems and the corresponding results. For baseline, we use the plain transformer model that is initialized randomly without using a pre-trained model. The BERT encoder and BERT-fused are mentioned on page 5. The next three models are mentioned on previous page. The performance of BERT encoder and BERT-fused are significantly higher than the baseline model and are comparable to the two teams in the shared task. This shows the effectiveness of using the pre-trained model. The BERT encoder full ensemble model makes an F-score nearly 5 points higher than the highest performance model in the shared task. However, there is no improvement for the BERT-fused full ensemble model compared with the single BERT-fused model. We find that the performance of the BERT-fused model depends on the warm-up model. The performance drops when we try to warm up the BERT-fused model from a weak baseline model. And we didn't use warm-up model in this work. Therefore, the BERT-fused model may perform better when warmed up from a stronger model. For the SOTA result, both the precision and the recall are comparatively high, and they therefore obtain the best F-score. Additionally, the precision of the models that use the pre-trained model is lower than the models proposed by the two teams. Conversely, the recall is significantly higher. To understand the error distribution of Chinese GEC, we annotate 100 sentences of development data and obtain 130 errors. We have 5 kinds of error: B, CC, CQ, CD, and CJ. B denotes character level errors, which are mainly spelling and punctuation errors. CC, CQ, and CD are word level errors, which are word selection, missed word, and redundant word errors, respectively. CJ denotes sentence level errors, which contain several complex errors, such as word order and lack of subject errors. Based on the number of errors, it is evident that word level errors CC, CQ, and CD are the most frequent. We show some examples here. The underlined tokens in examples are detected errors that should be replaced with the tokens in braces. Last, this table shows the detection and correction results of the BERT encoder and the BERT-fused models for each error type. The two models perform poorly on sentence-level errors, denoted as CJ, which often involve sentence reconstructions, showing that this is a difficult task. For character-level errors B, the models achieve better performance than other error types. Compared with the correction performance, the systems get better detection performance, showing that the systems address error positions appropriately. As conclusion, in this study, we incorporated a pre-trained model into an encoder-decoder model using two methods. On Chinese GEC tasks, the experimental results demonstrate that the usefulness of the BERT-based pre-trained model in the Chinese GEC task. Additionally, our error type analysis showed that sentence-level errors remain to be addressed. That's all. Thank you.